Alright, in this video I'll be doing a mock midterm 2 for Math 2B. This was made by one of the professors at UCI. Okay, so let's dive right in. I took a peek at some of the problems. Some of them are a little bit challenging or tedious. Sometimes I think tedious is challenging because there's a prone to error when there's lots of tedious work. So let's just get started right away. Okay, I'll be solving them live as per usual. So I might make mistakes along the way. I do have to key though, so I can check my answers. Okay, let's start with number 1. The first one's easy. We're asked to evaluate this guy, sine squared x dx. Okay, how to do that? Well, we know we have to use the half angle formula that you should memorize. That'll be 1 minus cosine of 2x dx. Okay, that's the half angle formula. This is easy to integrate. By the way, if you don't remember if it's minus or plus, a quick way to check is by plugging in x is 0, because we know sine of 0 is 0. Sine of 0 squared, that's 0 still. So this guy should be 0 also. So 1 minus cosine of, when x is 0, then it's cosine of 0. So it'll be 1 minus cosine of 0, so 1 minus 1, which is also 0. Okay, if it's plus, it'll be 1 plus cosine of 1. I mean, cosine 0, which is 1. So 1 plus 1 is 2. I had a brain fart there. 2 over 2, then it's 1. So that'll be, plus would be cosine, minus would be sine. So that's a quick way to check. Okay, so this guy is easy to integrate. That's simply just x minus half sine 2x plus c. Okay, and then you could distribute, but I will leave that up to you. Okay, that's the answer for the first guy. That one was easy. Okay, 1b, we have the integral of tangent to the 5th x secant cubed x dx. Okay, so the book, and maybe your professor tells you to memorize some rules for techniques for tangents and secants, integrals with tangent and secants. Honestly, I don't memorize those. I never remember them. Those are more tricky to memorize than the sines and cosines. That one for sine and cosine is odd power. That's the easy case. If it's even, then you have to use half angle formula. That's not too bad. This one is like even power of something and odd powers of something. It's too complicated. I don't remember those. Okay. So I just usually play around with the integral. If we are able to save a factor of tangent and secant, that would be great. Or if we save a factor of secant squared, that would be great. Because if we let u be tangent, du will be secant squared. So that's one of the techniques. The other technique is save a tangent and secant, because if we let u be secant, du is secant tangent. Okay? So in this particular case, I see that maybe we can save a tangent and a secant. Because when we do that, then tangent will be to the 4th and even power. Secant also will be to some even power. It'll be secant squared, right? So let's do that. Tangent to the 4th x, secant squared x. We saved a tangent and secant. I'm running very crooked, but that's okay. Okay, let's do that. Okay, so when we do this, we see, oh, we're kind of on the right track, because if we let u be secant, du would be secant tangent dx. Okay, so what's missing is this tangent to the 4th. We can use the identity. It's 1 plus tangent squared x is secant squared x. We can use this identity. Okay, so tangent squared is secant squared minus 1. So we can say it's secant squared x minus 1 squared secant squared x tangent x secant x dx. Okay, so we change this tangent to the 4th to secant squared minus 1 quantity squared, because that's be the same. Okay, so here we let u be, we said secant x, du, my pen is running out of ink. Let me change pens, sorry about that. Give me a few seconds. black pen. It's a bit smaller in the tip size, but that's okay. du would be, we said u is secant x, so du would be secant x tangent x dx. Okay? So we can write this integral as, oh, this guy is not, all my pens are running out of ink. Okay. We substitute, it'll be u squared minus 1 squared times u squared du. Okay? U is secant, so u squared minus 1, another u squared, secant tangent dx, that's du. This is easy to solve. We can FOIL it out first, so u to the fourth minus 2u squared plus 1 times u squared du. Okay, let's move over here, which is equal to, that is integral of u to the 6th minus 2u to the 4th plus u squared du. We integrate, we would get 1/7 u to the 7th minus 2/5 u to the 5th plus 1/3 u cubed plus c. And then we back substitute, we said u is secant x, so it'll be secant to the 7th power over 7 minus 2 times 2/5 secant to the 5th plus secant cubed over 3 plus c. That's our answer over there. This is a 7. Maybe double check my answer is correct. Yes, that's correct, okay? So the trick here was, again, I don't memorize those rules, but it looks like when we save a factor of tangent and secant, like we did here, the remaining powers are even, so that's a good sign because we can use the identity to make everything in terms of secant, which we did there, except the secant tangent. So then we can make the substitution. This integral is easy to solve. Okay? So that was that one. Next, let's move on. Okay. Let's do 1c. We have integral ln of x squared plus 1 dx. How do we solve this? Let's go down our techniques of integration. Is a substitution? Doesn't look like it because if we let u be ln of this guy, there's no signature of the du. Similarly, if we let u to be x squared plus 1, there's no signature of 2x dx, something like that. So probably not u substitution. Integration by parts, it might be because we should know that we have to use integration by parts to evaluate the integral of ln x. So that's possible. It's obviously not a trig integral. It's probably not trig sub because even if we do a substitution, it'll be natural log of some trig function, which that complicates things. So probably not that. It's not partial fractions. So we are left with integration by parts. So let's do that. So how do we choose a u? How do we choose a dv? Well, if we let dv to be ln of x squared plus 1, that's the same integral, so we don't want to do that. We don't know how to evaluate that. So we have to let u be ln x squared plus 1, and dv would be what's left, dx. So du would be 1 over x squared plus 1 times 2x. We need to chain rule, and dx. And then v would equal to just x. Integration by parts says uv minus v du. So we say, we say it's uv, so x ln x squared plus 1 minus, this would be v du, so we have a 2 in the front, integral of x squared over x squared plus 1 dx. Does that look correct? I think that is fine, okay? So how do we solve this guy? We can actually move the 2 in. Maybe that'll be easier. So this guy, how do we solve this? This is the tricky and tedious part. We can do long division to simplify this a little bit. So remember how to do that? inside goes the top, outside goes the bottom. Okay, so how do we do this? We multiply this guy by 2. So it'll be minus 2x squared plus 2 in parentheses. So we're left with minus 2 as the remainder. Okay, so we can rewrite this as, so this guy stays the same. We can rewrite this integral as the integral of the quotient, which is 2, plus the remainder over the divisor. So it'll be minus 2 over the divisor dx. Okay, so we do that. This integral of 2 is easy. This guy is also easy, that's just arctan. You should be able to recognize that. So we have, so it'll be minus, in parentheses, that would be 2x minus 2 arctan x plus c. Okay, so we simplify a little bit. The first term is still the same. We'll get minus 2x plus 2 arctan x plus c. And that's our answer. Okay, so the trick here was integration by parts, because that was the last technique when we went down our list in our head. We ended up with this after we did integration by parts. This guy, we had to use long division to simplify. We got this. This is easy to solve. Okay? So that's how we do that one. Okay, so here's another, this might take the whole page. So let me just move on to the next page. 1D. This integral looks intimidating, but let's do it. Okay, this integral. So likely we have to use partial fractions because there's a polynomial over a polynomial. Okay, but first we see that the degree of the top is more than the degree of the bottom. Similar to the last problem we saw. They were the same though. This one is, one's bigger than, the top is bigger than the bottom. So we have to use long division once again. We don't like long division, or I don't like long division, but let's do it. Okay, the dividend is, I believe the top is called the dividend. That's on the inside. The divisor is at the outside. Okay, so same technique. To get rid of the x squared, we have to multiply by x. So it'll be minus x cubed, because we distribute to each term, minus 3x squared plus 2x. We subtract this. What do we get? The x cubed would go away. We get 4x squared minus 12x. Sorry, that would not be minus 12. That would be minus 13x. And then we bring down the 7. Remember long division? We bring down. Okay, so then this one, now we multiply by 4. So it'll be minus 4x squared minus 12x plus 8. When we do that, 4x squared minus 4x squared is 0, minus 13x plus 12x, that's minus x, plus 7 minus 8, that'll be minus 1. We can't do anything else. Okay, so we can rewrite this integral as x plus 4, that's the quotient, and then the remainder. So plus minus x, or we do minus plus x plus 1. We can write it like this. We can factor out the minus sign. So that's what we did. So we have x plus 1 over the divisor, x squared minus 3x plus 2 by dx. Okay. So we're getting closer. These first two terms are easy. This one, now let's try partial fractions. So the top is x plus 1. Bottom, if we factor, it will be x minus 2, x minus 1. Okay, so if we break up to partial fractions, it'll be a over x minus 2 plus b over x minus 1. Something like that. Okay, so we multiply both sides of this equation here by the denominator. We get x plus 1 is equal to a times x minus 1 plus b times x minus 2. The quick way to solve this, we plug in x as 1, then this term would go away. We get minus b is 2, or we get b is minus 2. Okay? Then we plug in x is 2. This term would go away. We get a is equal to 3. Okay? So we can now rewrite this integral as x plus 4 stay the same. Now this guy can be written as, so don't forget your minus sign, written as the partial fraction, so it'll be, let's do it in parentheses, a is 3 over x minus 2, b is minus 2 over x minus 1 by dx. Like this. Okay? Now these are easy to solve. Let's distribute that minus sign first. So x plus 4 minus 3 over x minus 2 plus 2 over x minus 1 by dx. Okay? Let me double check I'm on the right track. I think so. Okay, let's integrate. Integral of x is just x squared over 2. Integral of 4 is just 4x. Integral of this guy is just log, right? So ln of x minus 2 plus 2 ln of x minus 1 plus c. This should be your answer. Let me check. Yep, I got the same thing. Okay, so the tedious part here obviously was the long division. Once we got that, that's over here. We do partial fractions for this guy over here, which is what we did here. Okay, and then after we did the partial fractions, this guy's easy to integrate. Power rule, log, log. Okay. All right. Let me move on to another page. I'm not sure if I can fit the next problem on here. Okay. So 1e, we have the integral of x over square root of x squared minus 9 by dx. Okay, so just by process of elimination, we haven't used trig sub yet, so that's likely what to use. And just from my experience doing it, this is probably trig sub. I would have thought of it too. Because it's something squared minus something squared under square root. That hints to me a triangle. Okay, so if you see me do trig sub before, I always set the triangle first. We know that since it's something squared minus something squared, x would be the hypotenuse, 3 would be one of the sides, and square root of x squared minus 9 would be the other side. Okay, if you do the Pythagorean theorem, this guy will work out, okay? So we want to sum everything in this integrand in terms of theta. We need x, we need dx, we need the square root. So for x, how can we get that in this triangle? Secant theta is x over 3, so 3 secant theta is equal to x. 3 secant theta, tangent theta, d theta would be dx. Okay? And then we can also substitute this square root term. How can we get that in a triangle? We know tangent is square root over 3. So 3 tangent theta is square root. Okay, so let's substitute everything in this integral in terms of theta. X we said is 3 secant theta. Dx is 3 secant tangent. Okay, and then the bottom we have 3 tangent theta. Okay, so we know that tangents can cancel. One of the 3's can cancel. So we simplified the integral to 3 secant squared theta d theta. Okay, that's easy. Integral of secant is just tangent. Put plus c, don't forget that. We need to back substitute. So we can get tangent from the triangle. We also notice that we use 3 tangent theta already here. So that's just square root of x squared minus 9 plus c. Okay, and then you can always double check by differentiating as always. We differentiate the square root with respect to x. What do we get? We get 1 over 2 square root of x squared minus 9, so there'll be a 2 here, times derivative inside, that'll be 2x. So the 2 up there, those 2's would cancel. So we know we got the correct answer. Okay? So that was not bad at all, that trig sub. Okay, let's move on to 3a. They skipped 2. It might have been an arc length problem. But, okay, let's continue. Integral from 1 to infinity of ln x over x squared dx. Okay, how do we solve this improper integral? Let's use our techniques of integration. Is it by parts? It might be, because we have a product of two functions. One's a log, so that might be our u, and dv would be 1 over x squared. Okay, it's not a trig integral. It's not a trig sub, not partial fraction. Is it a u sub? Would that work? If u is ln x, du would be 1 over x dx. That would be like du. It would not be du squared, actually. So no, that would not work. So we're stuck with integration by parts, likely. So let's try that. U would be, let's do ln of x. Du is 1 over x dx. Dv is whatever's remaining, so dx over x squared. So v is minus 1 over x. Okay? So integration by parts says uv minus v du, so minus ln of x over x, that's uv, minus integral, so evaluate that from 1 to infinity, we're just going to keep that until the end, minus the integral of v du, so it'll be plus, because of this minus sign and this minus sign, this would become a plus, 1 over x squared dx from 1 to infinity. Okay? That's simple to evaluate. So minus ln of x over x. That would just be minus 1 over x. We did it over here, actually. Okay? So that'll be minus 1 over x. Then we evaluate this from 1 to infinity. Okay? So maybe we can do a limit notation here. Limit as t goes to infinity of, is it two minus signs? Let's confirm. Okay. Of minus ln of x over x minus 1 over x from 1 to t. Okay. Let's do fundamental theorem of calculus. Limit as t goes to infinity of minus ln of t over t minus 1 over t plus, because it'll be minus these two terms, they're both negative, so it'll be plus. Okay? Plus ln of 1 is 0, so 0 over 1 would be 0 plus 0 plus 1 over 1 would just be 1. Okay? So we know that limit as t goes to infinity of this guy is 0. That's easy. That's a 0. So it'll be equals 1 plus limit t goes to infinity of minus ln of t over t. How do we find this limit? I need to shift this up somehow some more. Let me shift this lower. Okay. We can do L'Hopital's rule for this guy. Okay, let's move the minus sign actually in the front. Limit as t goes to infinity. When we do L'Hopital's rule, we get 1 over t over 1. Okay, at this minus sign move to the front, derivative of ln is 1 over t, derivative of t is 1. When we take limit as t goes to infinity of this guy goes to 0. Right? This guy goes to 0. Yeah, so it'll be, let me not cross that out. So it should be 1 over t. It'll be equal to 1 minus 0, which is 1. Sorry about that. Bad notation. So the limit as t goes to infinity of 1 over t is 0. So 0 over 1 is 0. So that's here. So 1 minus 0 is 1. So this integral converges to 1. Okay? Let's do the next improper integral. 1b, we have integral from 0 to 2 of 1 over x minus 1 cubed dx. Okay. Why is this an improper integral? There's a discontinuity at 1, so we have to write this as integral from 0 to 1 to the left of 1 over x minus 1 cubed dx, and then plus integral from 1 to the right. Is it 1? Did I get the notation right? Let me double check. It should be... if it's the upper limit, it's from the left. Yeah, I think this is right. So 1 to 2, 1 over x minus 1 cubed dx. We have to write it like that. So let's solve the first improper integral from 0 to 1 minus. Okay. This would just be power rule after you let u be x minus 1. So that would be, it'll be x minus 1 to the minus 2 over minus 2. Okay, evaluate this from 0 to 1 from the right. Okay. So we could write this as limit as t goes to 1 to the right of x minus 1 to the minus 2 over minus 2 from 0 to t. Okay, this guy, we can factor out the minus half actually. Then that would be limit as t goes to 1 minus 1 from the left of, so this would be, we plug in t, that would be t minus 1 to the minus 2 minus, we plug in 0, that would be so be minus 1 to the minus 2. Okay, I believe that's it. Let me double check my math is correct. We factor out the minus half, FTC, so that's fundamental theorem calculus, t minus 1 to the minus 2, and then minus 0 minus 1, which is minus 1, to the minus 2. I think that's correct. When we evaluate this, what happens? Okay, let me double check the key actually, that I'm on the right path first. Yeah, okay. This limit is easy. That's just minus 1 to the minus 2. That'll still be 1. So this will still be a minus 1. Now let's rewrite this as limit as t goes to 1 from the left. This would be more clear. Like this. So as we approach t from the left of this guy, would it be positive infinity or negative infinity? From the left means smaller than 1, so for example 0.999, 0.999 minus 1 squared, that will always be positive. So it'll be positive infinity minus 1, so that'll be positive infinity, but there's a minus sign here, so it'll be minus infinity. Okay. Now, we know that it's divergent because it's already infinity. But let's just evaluate the other improper integral from 1 plus to 2, 1 over x minus 1 cubed dx. We would get the same antiderivative, except the limits of integration are different. So we can rewrite this as limit as t goes to 1 from the right of, let's move the minus half to the front this time. It'll be 1 over x minus 1 squared. Evaluate from 0 to t. Sorry, this is t to 2. These are the correct limits. now. Okay, so when we do that, we get minus half. Limit as t goes to 1 from the right, it would be, we plug in 2, that would be 1, minus, we plug in t, that would be 1 over t minus 1 squared. Okay? This one, when t approaches 1 from the right, so numbers bigger than 1, so for example 1.001, well, it's squared, so regardless, that would be, this term would be positive. 1 minus positive infinity, that would be negative infinity. Negative infinity times another negative, this would be positive infinity. Okay, so we technically would get infinity minus infinity. That in itself is indeterminate, so we can say it's divergent. We already knew from one of them, but does it go to positive infinity or negative infinity or neither? This guy, it's infinity minus infinity. So divergent to neither plus infinity or minus infinity. Neither nor it should be. That's correct grammar. Okay, so that's how we answer this. So to recap, this is a long one, kind of long one. We know that this was an improper integral because there's a discontinuity at 1, so we have to break up the improper integral from 0 to 1 to the left, and then 1 from the right to 2. Okay, so we had to do that, and then we solved both improper integrals individually. One of them we got minus infinity, the other one we got plus infinity. So even if you just solve one of them, we already knew it was divergent. Okay? We solved both of them, and we saw that one of them goes to minus infinity. The other goes to positive infinity, so we don't know what this diverges to. Okay? So we're not sure whether, we don't know what it diverges to. So it doesn't diverge, it's divergent, but to neither plus or minus infinity. We're not sure. Okay? That's how we answer that problem. Okay. Actually, that was 3b also. So number 4. Okay. We're determining whether these sequences converge or diverge. If they converge, say what limit it converges to. If it diverges, similarly, like what we did here, we're to say if it goes to minus infinity, to plus infinity, or neither. Okay? So the first sequence we have is a sub n is pi to the n. Okay? We say limit as n goes to infinity, a sub n. Okay? We know that this is positive infinity. Okay? Why? Because what is the key actually has a not clear reason. We know that to justify, x to n converges for x less than 1. Okay, we're gonna say that as our justification. Pi to the n, so pi is like 3.14. Okay, so exponentially, as exponential function, as that goes to infinity, that goes to, so you can even justify it graphically, maybe. You know, pi to infinity looks something like this. So as n goes to infinity, this function goes to infinity. That could be another justification. Next, we have a sub n is 1 minus 1 to the n over 2. Okay? How do we solve this? Well, if we just write out terms, what would they be? The first term, if we start from n is 1, that would be 1 minus 1 to the n, minus 1 to the first power, so that would be 1 plus 1 over 2, that would be 1. The second term, when n is 2, then this minus 1 squared is positive 1, so it'll be 1 minus positive 1, that'll be 0. And they'll actually alternate from 1 to 0, like that. Okay? This is A1, A2, A3, so on and so forth. Okay? So this guy diverges. Okay. It doesn't diverge to, again, so we say it doesn't diverge to plus or minus infinity. So we again state that because the question asked that, to neither plus infinity nor minus infinity. Okay. So I didn't write exactly the question asked for, but I'm saying it out loud. It's good enough if you know it's divergent, but this particular professor wants you to write either to plus infinity, minus infinity, or neither. Okay, usually they don't, as far as the midterms I've seen, they don't usually ask that. Okay. For C, a sub n is e to the sine of n over n. Oh. How do I solve this? Limit as n goes to infinity, a sub n. Well, we can actually do the squeeze theorem for this. We know that sine n is between 1 and minus 1. Okay, that's where the range of sine is. So we know e to the minus 1 is less than or equal to e to the sine of n, which is less than or equal to e to the first power. We exponentiate it everywhere, and then now we multiply by 1 over n everywhere. E to the minus 1 over n less than or equal to e to the sine of n over n less than or equal to e over n. Okay? So we know that limit as n goes to infinity of e to minus 1 over n. E is just a constant. So limit as n goes to infinity of 1 over n, that's 0. So constant times 0, 0. Limit as n goes to infinity of e over n, same reason, 0. E is just constant, so 1 over n. Limit as n goes to infinity of 1 over n is 0. So therefore, by squeeze theorem, limit n goes to infinity, a sub n is also equal to 0. So it converges to 0. Okay, so that's how we solve that one. For D, a sub n is square root of n plus 1 minus square root of n. So we have limit as n goes to infinity, a sub of when n goes to infinity, we would get infinity minus infinity, so that's indeterminate. So how can we solve something like this? Remember, when we have square roots, we like to use the conjugate. So this is the original. We multiply by the conjugate. That's square root of n plus 1 plus square root n. We do it to the top and bottom so that it's equivalent. Okay, so when we do this, we get limit as n goes to infinity of, we get n plus 1 minus n on the top, square root of n plus 1 plus square root of n on the bottom. Okay, so this and this would cancel. Now, as we take n goes to infinity, this guy goes to 0. Okay, so this guy converges to 0. Okay, that was easy. For E, this one's also easy. N cubed e to the minus n. So limit as n goes to infinity of a sub n, we can write this as limit as n goes to infinity of n cubed over e to the n. When we write it like this, we have infinity over infinity, that's indeterminate. We can use L'Hopital's rule. That'll be 3n squared over e to the n. We use L'Hopital's rule again. That'll be 6n over e to the n. We just keep differentiating the top and the bottom separately. That's what we did. So derivative of n cubed is 3n squared. Derivative of this guy is 6n. Okay, derivative of e is just e. Okay, so we do L'Hopital's rule one more time. And limit as n goes to infinity, because it's still infinity over infinity. Okay, so that's another thing. Over here is infinity over infinity. Over here is infinity over infinity. We can keep using L'Hopital's rule. 6 over e to the n. Now, when we take this limit, as n goes to infinity, the bottom gets bigger and bigger, so this fraction gets smaller and smaller. So this goes to 0. Okay, and converges to 0. Okay, last problem, I believe, for F, yes, okay. We have, a sub n is minus 1 to n. over 2 square root of n. Okay, so we can first find the limit as n goes to infinity, absolute value of a sub n. Okay, we can do that. When we do that, limit as n goes to infinity, when we take the absolute value of a sub n, this alternating sign of minus 1 to the n would go away, so we just get 1 over 2 root n. This is easy. As n goes to infinity, that goes to 0. So because this guy goes to 0, we know limit as n goes to infinity, so n is also equal to 0. So this guy converges to 0. Okay? So that was not bad, all these sequences. So the challenging parts were the integration problems, in my opinion. You needed long division for them. That's the only thing, okay? So as always, if you have any questions, feel free to leave it in the comments. If this video has helped you in any way, please smash that like button and please subscribe to the channel for more videos like this.